Hi all, good to see you all in a new topic through the social media platform. So I'm Aishwarya, Assistant Professor in the Biomedical Department, working in Emmanuel as a JJ College of Engineering. So today we are going to discuss a new topic, CISC Architecture. So let's move into the section. So what is actually CISC? The CISC stands for Complex Instruction Set Computing, a processor design that uses a large set of instructions capable of performing multiple operations in a single command. So multiple operations can be done using a single instruction. Okay, so multiple operations can be done by using a single instruction is done for this CISC. So computer architecture which determines how a processor executes the instructions. Okay, so computer architecture that is has two types of processors. The one is the CISC. CISC stands for Complex Instruction Set Computer, and next one is the RISC, which means Reduced Instruction Set Computer. So the CISC which we are going to see today in brief. So the CISC was developed to reduce the number of instructions required to execute a program by allowing one instructions to perform multiple operations. So the CISC was developed to reduce the number of instructions required to execute a program by allowing one instructions to perform multiple operations. So what is CISC? You have a good idea, right? So CISC stands for Complex Instruction Set Computer, is a processor architecture that provides a large number of complex instructions. A single instruction can perform multiple low-level operations such as loading data, performing arithmetic, and storing the result. So these are the basic things which is done by using this CISC. Okay, that is, the single instruction can be used for doing multiple operations which can be performed multiple low-level operations such as loading data. So the multiple operations may be loading data, performing arithmetic, and storing the result. For an example, let me say something. Add A comma B. Okay, for example, now this instruction, what will the process is done there? First, the instruction may fetch the data A. Next, it fetch the data B. Again, what will the performance be done there? It performs addition, because in the example we have given add, right? So it performs addition. Again, what happens? It stores the result automatically using the only one instruction. We have given only one instruction, add. Okay, but it will automatically fetch A, one instruction. It fetch B, second instruction. Again, it performs addition, third instruction. Again, it stores the result automatically, fourth instruction, right? So the four operations were done by using the only one instruction, add A comma B. Okay, so this is the best example for this CISC operation. So some of the key features, see, they are complex instructions, variable length instructions, direct operand manipulation, extended instruction set. So complex instructions means each instructions can perform multiple operations, reducing the number of instructions needed for a program. So the next is the variable length instructions, which means the instructions can vary in size depending on the complexity of the operations. So the third one is the direct operand manipulations. That is, CISC allows operations directly on memory operands, minimizing memory accesses. So it reduces the memory accesses. Again, extensive instruction sets, which supports a wide range of operations addressing modes, data types, making it versatile for complex tasks. So these are the main key features in which it is simply said as it has large instruction set, means it supports many instructions to do the single operations. Again, variable length instructions means the instructions may be of different sizes, can do operations. Complex addressing modes means it provides multiple ways to access the data. Again, memory to memory operations means it directly stores on memory without the use of registers. Okay, so registers are not mandatory here. Again, micro-programmed control unit means the micro codes are used to execute the programs or execute the instructions. Again, fewer instructions per program means it has single instructions can do multitask. That's what the main task, main feature of this CISC. Okay. So history of CISC is nothing but between 1960s to 1970s, the mainframe and many computer architectures like IBM System 360, PDP-11 and VAX. These are the microcomputers and mainframe computers names. Okay, were labeled CISC due to their complex instruction sets. These computers used CISC because of the complex instruction set. Okay, so in 1970s, the Berkeley RISC project highlighted that most programs used only a small subset of RISC instruction, leading to the development of RISC as a simpler alternative. Again, in 1981, the Intel 8088, that is Intel 8088, a CISC processor powered the original IBM PC, cementing CISC as the dominant architecture in personal computers. So it dominates by using the IBM PC. In personal computers, it is used to dominate the CISC usage. Now, the block diagram of CISC architecture, okay, it is nothing but it comprises with a register set, arithmetic and logic unit, it comprises with register set, arithmetic and logic unit, instruction decoder, microprogrammed control unit, control storage, that is the ROM is used here. ROM is nothing but read-only memory. Bus interface unit, address buffer, data buffer, and control buffer. Okay, so the main memory is given there. That is, it is called as the program. The main memory has the program where the instructions are, then the data is also there. So it is given to the input or output devices. The input or output devices may be which one? Keyboard, monitor, disk, printer. It can be the input and output devices. So from there, the address bus, it is a unidirectional. Unidirectional is only one direction, CPU to memory or to the input devices. Again, to the data bus, they are bidirectional, so it can be both given to data bus or to the input output devices. Again, to the control bus, they are also the bidirectional process, so they can give the data in both the direction, to the input data or to the control bus. Okay, here the first one, the register set, has general purpose registers, index registers, segment registers, point registers, and flag registers. Okay, so upcoming next we can see one by one in detail. So now I will explain you overall about the block diagram. Okay, so first in the register sets you have general purpose registers, index registers, segment registers, point registers, and flag registers. Okay, again in the arithmetic and logic unit you have ALU and status flags. Okay, again you have instruction decoder, microprogrammed control unit, again bus interface units. In the bus interface units only you have address buffer, data buffer, and control buffer. So what is this main register set will be doing? The register set stores data, addresses, and status the information. Okay, it stores the data first, again it addresses the information, again its status, that is in what condition the information is present there, it will status the information. Then the ALU, arithmetic and logic unit, is the CPU which performs the arithmetic and logical operation. As per the name denotes, it does the arithmetic and logical operations. Okay, again instruction decoder, it decodes instructions and generates control signals. Okay, the instruction decodes the decoder which decodes the instructions and generates the control signals to be controlled by the instruction set. Okay. Now, next one is the microprogrammed control unit. This one, the microprogrammed control unit, which generates micro operations using microprograms stored in control store. Okay, in the control store, there is control store is the ROM, that is read-only memory. There they are stored some microprograms. Okay, so that microprograms are used to generate micro operations. So the micro operations are generated by using the microprograms which are stored in the control store, that is in the ROM, by using the microprogrammed control unit. Okay, again next is the bus interface unit. The bus interface unit interfaces CPU with system buses. So the bus interface unit interfaces CPU with system buses. The bus interface unit interfaces the CPU along with the system buses which are provided inside the unit. So what are the buses here? As I shown here, the address bus, data bus and control bus. Okay, so in the picture it is defined as address buffer, data buffer and control buffer. No mistake in that, both are same. Okay, so the address bus, data bus and control bus. The address bus, what is the use of address bus here? Address bus carries the addresses from CPU to the memory of input output direction, that is only through the unidirectional shape direction, that is only one direction. It takes the system from the CPU to the input output devices or to the main memory. Main memory means where the instructions and data are stored. Okay, again, data bus. What is the use of data bus? It carries the data between the CPU memory and the input output device. Okay, means it is bi-directional. In between, it carries the data from main memory to input devices to the CPU, or it carries the data from CPU to the input output devices or to the main memory. Okay, they are bi-directional. Both the directions they can travel. Again, next one is the control buffer or the control bus, which carries controls and timing signals. So these are also bi-directional only. It carries the signal, it controls the signal, and it sets the signals using the timing. So it controls and change the time of the signal. They are also bidirectional. Okay. Next is input output devices. So what are the input output devices given here? Keyboard, monitor, disk, printer. So here keyboard and keyboard is the input device. Disk is also the input device. Monitor and printer is the output device, isn't it? So the peripherals are connected to the system. These are the peripherals which are connected to the systems are called as the input and output devices. Okay, do you get a good idea on the block diagram of CISC architecture? So it is the main memory which is given to the instruction cache. Then it is given to the control limit. Then the microprogram controls are done there. The arithmetic and logic queues are done there. Then the process buses are also used there. Okay. So some of the instruction sets, what are they? Some of the instruction sets there are. There are large instruction sets, variable length instructions, complex instructions, multiple addressing modes, memory to memory operations. Okay. Again, micro-programmed control unit, high code density, fewer assembly instructions, multi-cycle execution, rich instruction formats. All these are the characteristics of CISC having the instruction sets. Okay, so once again there are large instruction sets, variable length instructions, complex instructions, multiple addressing modes, memory to memory operations, micro-programmed control unit, high code density, fewer assembly instructions, multi-cycle execution, and rich instruction formats. Okay, these are the characteristics. So next, what are the addressing modes in CISC architecture? Okay. What are the addressing modes here? They are immediate addressing, register addressing, direct addressing, indirect addressing, register indirect addressing, indexed addressing, base addressing, base indexed addressing, base indexed with displacement addressing, relative, that is PC relative addressing. PC means personal computer or program counter related addressing. Okay, so let's discuss one by one. Okay, so the first one is immediate addressing. Immediate addressing is operand is a part of instruction itself. Okay, first one is immediate addressing. So the immediate addressing, the operand is a part of the instruction itself. That is the instruction format. The opcode is given and the immediate data is also given. For example, move R1 comma cache 25. So what will the R1 do? R1 is the opcode and R1 is the opcode and 25 is the immediate data here. Okay. The next one is the register addressing. So the register addressing, the operand is in the register. So which is the operand here? It is in the register. So the R1 is A5 and R2 is the data operand is in the register R2. Okay. Next one. Direct addressing. Direct addressing means the instruction contains the memory address of the operand. The instruction contains the memory address of the operand. The instruction following the operand direct address. Example C move R1, 1000H. So what will happen? This is the data format and this is the memory pool. So where does it belongs to? It belongs to 1000H. So for 1000H, what is the value? 45H. So this is the operand. Okay. The next one is indirect addressing. So for indirect addressing, address field points to memory location that contains the address of the operand. Okay, the address field points to a memory location that contains the address of the operand. So the instruction format is opcode and address. The example is new R1, 1000H. Here also, as I told, this is the memory and this is the data formats in which the address of operands are to be found out at the 1000H. So 1000H, what is the value you have given? 2000H. So that is the value and it is moved to the value R1. Okay. Next is register indirect addressing. Register indirect addressing. Okay, so the register indirect addressing means a register contains the memory address of the operand. Okay, the register contains the memory address of the operand. So what is the instruction format here? Opcode register. So example C, move R1, R2 means R2 has 3000H. So what is the operand here? 3000H has 7AK. So that is the R1 operand here. Okay, so what are the value you have here? That is moved to the next value. So where it is moved? To the R2. So R2 which you have the value 7A. So that is removed. Okay. Next one is indexed addressing. Index addressing is nothing but the effective address is the sum of the index registers and the address field. The effective address is the sum of the index registers and address field. So here what will you do? The instruction formats opcode and addresses, which is given as example move R1, 2000H of R3. So here the value 2000H is moved to value R3. So this is the value 01. 0010H. So this is the value for R3 and it is moved to 2000H. So that is the value for R1. So it is again moved to R1. Okay. Next is the base register addressing. So next is the base addressing means register addressing. Here the effective address is the sum of the base register and address field. Here what is the instruction format? As you can see, this is the opcode with the address. Okay, if example is R1 1500H of R4. So here what is the effective address will be done as 1000H plus 1500H. It is equal to 2500H. So the number which is located in the 2500H is 6EH, which is stored in the R1 register. Okay. So again, next one is the base index register. So the base index register is the effective address is the sum of the base register, the index register, and the address field. Here you have the effective address is the sum of the base register. What is the sum of the base register? 1000. And then what is the index register here? Here 0020H. So what is the sum of them? Both is 1020H. So this is the effective address 1020H. This is 1020H. What is the value here? 9CH. So for that it is stored in the register. What is moved in the register? Register. So the next one is base indexed with displacement. So the effective address is the sum of the base register. Sum of the base register 1000 plus index register 0010H plus. Displacement, what is the displacement here? 0020, which is what? We have the sum all these three and we get 1030H. So this 1030H is the value and there it is moved to the value R1. Okay, it is moved here. The next one is relative PC relative addressing. PC means program counter. So the effective address is the sum of program counter and the displacement. So here the PC counter is 2000 and the displacement is 0020H. So they both are added and we get 2020H. So the 2020H has the value 75H. That is the target address, which is the output. Okay. So now we are going to say about the memory organization. Okay, the memory organization here is the block with registers, ALU control unit, address bus, data bus, and then we have control bus. So it has the block diagram, registers, ALU, then control unit. Okay, again it has another, that is buses. What are they? Address bus, data bus, and control bus. Okay, it eventually has a main memory block with program instructions and data within it. Okay, so it is then given to the input or output devices. Okay, so these are the memory organization systems where it is used. So these are things which are found in the memory organization. Okay. So memory organization, the memory is actually divided into operating system, program code, data segment, heap, and stack. Okay. Here first it will read the operation. Main operation here is it will read the data. That is the CPU reads data from the memory. Again, the writing options happens. That is the CPU stores the data into the memory. That is the writing option. Again, the memory to memory operations happen. That is the unique feature of system. That is the complex instruction set controlled as the unique operation of memory to memory operation. Okay. For example, if add, for example, you want to add something. Okay, so how will you add? 1, 2. What will you do there? Processor reads both the operands directly from the memory and then it is stored alternatively. Okay, that's what happens there. Okay, so this is what happens in the memory to memory operation of organization. So next one is the register. What type of registers are they? Okay, so the CISC also has registers. As I already told in the block diagram, we were learning about the registers, right? So what are the registers there? We are going to discuss them in deep. Okay, in the block diagram, we have simply said there are some types of registers, and now we're going to go through that again. So what are them is CISC registers. They have general purpose registers, control registers, and then memory registers. Okay, the general purpose registers, control registers, and memory registers general purpose registers actually has AX, BX, CX, and DS. So what are they actually? AX, BX are the examples in Indian 886 processes. Okay, they are used to store the general and temporary data. They are used to store the temporary data. Again, control registers. They have PCRIP or port ID. Okay, they are used to store control registers. So they are used for control registers. That is, IR means instruction registers, which stores the currently executing instructions. Okay, the previously used programs are not there. The currently used instructions is stored in IR. That is the instruction registers. Then PC means program counter. That is, it stores the address of the next instruction. Okay, it stores the address of the next instruction. Again, the memory register. What is actually memory register? It has MAR means memory address registers, and MDR means stores memory data registers. Okay, MAR means memory address registers, and MDR means memory data registers. So when you use a memory address register, the memory address register stores the data. It stores the address of the memory location. It stores the address of the memory location. So what about memory data register? It stores the data being transferred. The data which are being transferred are stored under memory data registers. Okay. Again, the control registers also can be divided into. So what is this? Again, SP. SP means stack pointer, which points to the top of the stack. Okay. Again, BP is the another type of register, and flag register is also used to store the status flag. For example, zero flag, carry flag, sign flag, overflow flag. All these flags are stored in this flag register. Okay. And also the SP is divided into index registers and segment registers. In where the index registers has SI and DI, and the segment registers ES, DS, SS, ES. These are other types of stable registers which are used to store the instructions in the data and memory. So these are the registers. So registers are nothing but CP registers is general purpose control registers and memory registers, and they are used to store temporary data. And the control registers used to store the data which are using the executor and the program counter systems. And the memory registers used to store the address which is stored and the data which is being executed. Okay. It also has SP and BP and flag registers which is used to store the temporary data. Also has some segment registers and index registers. Working of the CISC processor. How does the CISC processor working happens? Because the processor follows several steps. Only by these steps, processes can be worked properly inside a CISC processor. So what are they? The main memory have to fetch, after giving the main memory, it fetches the instructions. Again, it instructions instruct the register, and also it instructs the decoder to decode. Again, it is given to micro program to control unit. Then it is given to the register where ALU to the memory. As in the block diagram, we have seen the same step. Then it stores the result, and the next instruction is being fetched or executed. Okay. So these are the steps used in the working of CISC processor. So first step is fetching. Fetching is nothing but the instruction is fetched from the memory. What are the things we need? The instructions must be fetched from the memory. Then it decodes. Step 2 is the decoding process. It decodes the control interrupts the instructions. So for decoding, what happens? The control interrupts the instructions. And step 3 is it fetch the operands. What operand should be used? That should be fetched. So what are the operands? The operands are obtained from registers or memory. So the operands, there may be registers or memory. So the operands which are used in the registers and memories are obtained gradually. Then it executes. What execution has happens here? ALU performs the required operations which is need to be executed. Not all operations, only the required operations which is needed to be executed. Okay. Next, it stores the result. What happens? It stores the result the result is written back to the memory or register. So the information which is needed is taken from the memory and register. Again, it happens execution, and after execution, the results are stored back to the memory or the registers where it is taken back. Okay. So these are the process which has been done. That is a very simple instruction means start the program, fetching the instruction, decoding instructions, fetching the operands, executing the instructions, again storing the result for the next instructions will be done. That is the next fetching or next process or next execution happens when start. Okay. So these are the process. What is that? Once again, starting the program, fetching the instruction, decoding the instruction, fetching the operands, executing the instructions, storing the result. So it goes to the next instruction. Okay. So this is the CISC processor. Okay. Now, before going to advantages, let me explain you a small example. Okay. So example is add M1 comma M2. What will happen if you're adding M1 comma M2? So this is the instruction add M1 comma M2. So what is the processor will do here? What the processor will do here? Do anyone know what will the processor do here? What does the processor do here? First, the processor reads M1. Okay. Next, what happens? The processor reads M2. First, it reads M1, then it reads M2. Then what happens? The adding process will begin. It adds both M1 and M2. Then it stores. So this is what the process of which one? CISC. That is, it has a simple instruction add M1 comma M2, but it does multiple operation, like it reads the M1 operation number 1, it reads the M2 operation number 2, it adds both M1 and M3 operation 3, again finally it stores the results operation 4. So 4 operations are done under a single instruction. Okay, we understand this now? So now the advantages. Reduced program size. As per the instructions are reduced, the program size can also get reduced. Okay, no problem in sizes now. So see, the programming is very easy, right? When a command is given, it automatically will what types of the operations should be done there. It is easily programmed, right? So this is one of the best example. Again, high code density. For big codes also we can do this method. CISC architecture very easily. Again, memory to memory operation. As I told already, that is the biggest advantages in this CISC architecture. Rich addressing. We have explained a lot, 8 or more types of addressing modes we have explained, right? So it has rich type of, that is many types of addressing modes can be used in this CISC architecture. Again, fewer instruction per program. Fewer instruction means what? For a single program, only a less amount of instructions can be given. Okay, large number of instructions are needed, like that. Compulsion is there. You can use only less instructions, and you can do many multitasking operations can be done using this CISC architecture. Again, compatibility. Comparing with other programs or instruction sets, this is very comparatively easy. Then efficient for complex application. For complex applications, they may be using large type of programs, right? For them, the multi operations will be done at any time. So for that, the simple instructions can be multi operations, so that the program, complex programs can also be made very easily, so that if they are easily done, then they can be efficiently used, right? So it is said that efficient for complex applications. Okay. Next is the disadvantages. What are the disadvantages here? It is complex hardware design. The complex design of hardware is so for disadvantages as we are doing this. The hardware designing is very complex process in this CISC architecture. Okay, unless that it is okay, but the hardware design is very complex. So variable length instructions here, the length of the instructions may be also high. Here, the length of the instructions may be also very high because with variable sizes, the instruction sets. So with variable length sizes, the instruction sizes can also get changed. Slower execution. Sometimes multitasking may get the execution time is very slower. So as the instruction is doing multi operations, there may be higher power consumption. That is one of the drawback here. Difficult pipeline implementation. The pipeline implementation is very difficult. Again, larger chip areas. What are they? It larger chip areas. In more heat generation, we need much processes or multitasking. Heat generations is more and higher manufacturing cost. Here, it is manufacturing of hardware is a little bit expensive. The common application is used in scientific community, multimedia processing, high-level programming languages, embedded systems for there. It is mainly used to give the scientific computing, multimedia processing, high-level programming languages, and even in embedded systems, they are very used. So the next is real-time applications where we are used in desktops, laptops, servers. Okay, very much used desktops, laptops, servers. So these are the real-time applications. So this is from desktop, laptops, and servers. So this is a server. This is the embedded systems. Okay, here it is mainly managed. So these are the types of PCs and laptops. Okay. So for these are equipments, they are used in modern optimizations, pipelining, and capture. So modern optimization is nothing but it is the execution of optimization techniques which are used very clearly. So pipelining is the execution of register to register and all the store instructions is called as the pipeline. So pipelining is having a register instructions, load instructions, and store instructions. That is from register to register. This is the instruction and CPU is the instruction and it stores the instructions. Okay, first it takes sections, then it stores the things, and then it stores the instructions. That's the pipeline. So real-world examples for Intel Police. So the real-world examples for this architecture is Intel 4 Ultra, Intel Ultra. Now it is very famous non-mobile techniques. It is AMD Ryzen. It is another type of chip. Okay, that is called as AMD Ryzen. So these are the real-time examples for this architecture. It is modern, world-based, and not for 70% it is present. Okay. So I hope you understand this is architecture. Do like and if you have any doubt in watching this video, please do it in the comments. Okay. Thank you. We will meet all soon. Nice to meet you. Bye bye. Thank you.